Welcome to this lecture on number theory. Today, we are going to explore a fundamental and fascinating concept called the prime counting function. If you have ever wondered how mathematicians keep track of prime numbers as they stretch out toward infinity and how this connects to the modern world, you are in the right place. Let us dive in and build our understanding from the ground up. To understand this concept, imagine you are walking down a long street where every house has a number on its door, starting from 1 and going up forever. You are a special inspector whose only job is to find prime houses. These are houses whose numbers can only be divided by 1 and themselves. You carry a mechanical clicker. Every time you walk past a prime house, you press the clicker once. If you stop walking at a specific house number, the total shown on your clicker is exactly what mathematicians call the prime counting function. Now that we have our analogy, let us look at the formal mathematics. The prime counting function is denoted by the symbol pi of x. Do not confuse this with the famous geometry constant 3.14. Here, the Greek letter pi simply stands for the word prime. This function outputs the exact number of prime numbers that are less than or equal to a given real number x. Because primes do not follow a simple predictable pattern, this is not a smooth curve. Instead, it is a step function. It stays perfectly flat and then suddenly jumps up by exactly 1 every time x reaches a new prime number. This brings us to the mathematical formula for the prime counting function. It looks simple, but it is very powerful. The symbol pi of x represents the function evaluated at the number x. The large Greek letter sigma represents a summation, which means we are adding a series of values together. The condition underneath tells us that we only consider prime numbers, denoted by p, that are less than or equal to our chosen limit x. The number 1 inside the sum means that for every valid prime we find, we add exactly 1 to our running total. As x increases, the total only grows when we cross a new prime. Before we calculate anything, let us see this visually. Looking at this graph, you can see exactly how the prime counting function behaves. The horizontal axis represents our input number x, and the vertical axis is the count of primes. Notice how the graph starts at 0 and remains completely flat until it reaches the first prime number, which is 2. At that exact moment, the graph jumps up by 1 step. It continues this flat then jump pattern forever, creating a staircase where the steps only occur at prime numbers. This makes it very easy to see that the function does not change value in the gaps between primes. Now that we understand the formula and the graph, let us see this with a concrete example. We are asked to find the total number of primes up to 10. We are given the upper limit, x equals 10, and we need to calculate the exact value of pi of 10. Using our formula, we set up the summation for all primes p that are less than or equal to 10. This means we will completely ignore any number that is 11 or larger and prepare to add a series of ones together for every prime we find in this range. Continuing with our calculation, our next step is to list all the positive integers starting from 1 up to 10. From this list, we must carefully identify which numbers are prime. You must always remember that the number 1 is not considered a prime number. Looking at the remaining numbers, the primes up to 10 are exactly 2, 3, 5, and 7. These are the only numbers in our range that cannot be divided by anything other than 1 and themselves. Now we simply count them up. For each of the 4 prime numbers we found, we add the number 1 to our running total. This is exactly what the summation formula instructs us to do. We have 4 primes, so we write down the number 1 4 separate times. Adding them together gives us our final calculated answer of 4. This physically means that if you look at a standard number line from 0 to 10, you will encounter exactly 4 prime numbers along the way. Let us try another example, this time with a decimal. We are given a non-integer upper limit of 17.5. We are asked to determine the value of the prime counting function for this decimal number. The input value does not have to be a whole integer. It can be any real number. We will use the exact same logical strategy as before. We set our upper limit to 17.5. And our formula tells us to find all whole prime numbers that fit strictly inside this boundary. Continuing our process, we list the prime numbers starting from 2 and stop just before we exceed 17.5. The primes in this range are 2, 3, 5, 7, 11, 13, and 17. The largest prime in this list is 17. We stop here because the very next prime is 19. Since 19 is strictly greater than 17.5, it does not get included in our list. The formula only cares about the primes that are less than or equal to our specific limit. To finish the problem, we count the numbers in our gathered set. We find there are exactly 7 primes. So, pi of 17.5 equals 7. Because there are no new primes between 17 and 17.5, the total count does not change. This shows that the function's value remains completely flat between the integers 17 and 19. Evaluating the function at 17 and at 17.5 will give you the exact same result. You might wonder why mathematicians care so much about counting primes. The prime counting function is the absolute foundation for understanding how prime numbers are distributed across the number line. At first glance, primes seem to appear completely randomly. However, studying this exact function led mathematicians to the discovery of the prime number theorem. This groundbreaking theorem shows that primes actually thin out in a very predictable way as numbers get larger, revealing hidden order in the universe of numbers. This predictable distribution we just discussed is not just a theoretical curiosity. It has massive real-world impact. It is the backbone of modern digital security. Every time you buy something online or send a secure message, your data is protected by encryption algorithms like RSA. These algorithms rely heavily on the properties of massive prime numbers. If we did not understand how to count and locate primes using functions like the prime counting function, secure internet communication would be completely impossible. Let us review the key takeaways from today's lecture. The prime counting function, denoted as pi of x, is a mathematical tool that tallies up all the prime numbers up to a specific limit. We saw that it operates as a step function, jumping up by 1 every time it encounters a new prime, and that the input can be any real number. Finally, by studying this simple counting mechanism, mathematicians unlock the deep, hidden patterns governing prime numbers, which ultimately secures our modern digital world. Great job following along.